here we go. So today we are going to look at page 2 of the problem set, and this one has to do with the law of conservation of momentum. Now, if you remember, we went through the law of conservation of momentum, and conceptually it's pretty simple. However much momentum you have before, some kind of event or collision, you got to have the same amount of momentum after. But because you don't always have the same number of particles all the time involved, we had 3 different scenarios for, I call them situations. We had the 2 to 2, 2 to 1, and 1 to 2. So what we're going to do here is we are going to take a look at the second page on this problem set, and we're going to try and work through the setup for a couple problems just to make sure you're comfortable with this, okay? And then what I'm going to do is, I think there's a total of 1, 2, 3, 4, 5, 6. There are 7 total problems on there. Once we're done doing a couple or setting up a couple, I'm just going to give you the rest of the time that we have left to work on them. Okay? So, here's what we're going to do first, though. I think we have problems 13 through 19. So we got 13, 14, 15, 16, 17, 18, and 19. This is the first thing that I would like you to do. And we'll just start with 13. Read through the description of 13 and tell me, I need somebody to chime in on this, and tell me what kind of situation do you think you're dealing with here in problem 13? Because once you can tell me that correctly, then you automatically know what's the equation that I should be using to solve this problem. So take a moment to read that. And remember, for those in video land, you can access this worksheet on the class webpage, on the worksheet page. Just click on the one, I think it says conservation of momentum. I will double check that here. So you go to physics, worksheets, and then on that menu, you can just click on the momentum worksheet, and it's page 2 of that one. Yep. Okay. Anybody have any thoughts? Taking a risk. Julian? Very good. Why?
Because it starts off with the kangaroo on the log and the kangaroo jumps off.
Perfect. When we look at this and say, what are the objects in the problem? There is the kangaroo and there is the log. And the idea is that they start the problem together with the kangaroo being on the log. And then it says the kangaroo jumps off the log, and then they become separate. So when people go, but wait a minute, you got a kangaroo and a log, they're together. How is that one? It's because they're together. Even though we might look at them and say, aren't those 2 different things? Sure, but they are connected together to begin the problem. All right, so for problem 13, it is a 1 to 2. Now, to make this problem number 1 a little more contemporary, what kind of common thing, although I don't see tons of them here on campus compared to other places, might you be able to kind of say, oh, it's like a person jumping off of this? Anybody know what I'm referring to?
Can you repeat the question?
There's a scenario for this that's a little more contemporary, because some people go, oh my God, a log and a kangaroo? But what do people occasionally jump off of that, they're together, but then they hop off And they might be actually moving around while they're on it, but they hop off it. Anybody think they know what a skateboard? Okay, now a skateboard is not going to be as big as the log, but it's the same scenario. Okay, now that's all I want to do for the moment. 14. What kind of situation we got? Any thoughts? It's a 1 to 2. What are the two objects?
The plane and the pilot.
Correct. But they start the problem all together. All right? So problem 14 is also a 1 to 2. All right? Oh, this is excellent. So I got 2 people who are out of the mix now. All right? The rest of you, the pressure is mounting. Actually 3, because Lily came in with her answer too. 15. Okay, why? What are the two things?
The dog and the boat.
Correct. And they start apart from each other, and then the dog jumps onto the boat.
Yep.
So that's a 2 to 1. Okay? 16.
One to two.
What are our objects?
Buses.
We have 2 buses. How do they start?
They start separate and then one collides with the other.
And then what's the key word in there that says what happens to them when they collide?
Oh, they move off each other. They move off together.
Okay, so what are we dealing? Our 2 objects are 2 buses.
Yeah.
Do they start together or separate?
Separate.
And then what happens because they crash?
They come together.
They come together. So what will it be? 2 to 1. Okay? I think I need to mix these problems up so it's not quite so predictable here. Okay, 17.
2 to 1.
Okay, what are our objects?
The cow and the carts.
Yeah, now, and each cow is on a cart, so you're going to have to pay attention here because when someone says, hey, what's the mass of one object? It's actually a cow and a cart together, and there's another cow and another cart that, and then they stick together. Okay, 18. This one, read very carefully. Okay?
You have to like take account for friction.
No. It's kind of worked in when you would solve this. Anybody who hasn't chimed in yet want to go for it? Okay, Matthew?
Maybe 2 to 1 2.
Tell me what you're thinking when you say that.
Because the arrow hits the target, it passes through the target stops, but the arrow keeps on going.
Okay, so what are our objects in the problem?
The arrow and the target.
The arrow and the target. So how do they start?
They start by traveling towards each other.
Okay, so they're separate from each other.
Yeah.
So that definitely means that we start with 2. And then what happens?
They collide, and then the arrow passes through the target.
Which means, does the arrow stay stuck to the target?
No.
No, it blows right through it. So when we're done, how many distinct objects do we have? 2. So that means this would be a 2 to 2. This one tends to throw people because most people, when you shoot an arrow at a target, it just goes in and sticks. Okay, 19. This one I'll open it up to anybody.
3 to 1.
3 to 1. This one's helpful in that it has a picture so you can see the 3 separate objects. But the key words is that says the carts stick together after colliding. All right? So, with this little list in mind, this should be helpful for you when you go to solve or try to solve each of these problems, because you'll already know what should the equation look like that you're playing with. Okay, everybody's good with this? All right, this is the moment if you need a picture with this, you take a picture. If not, you're like, I can always watch the video and I see that. Okay? So now what we're going to do is we will look at one or maybe two, and we'll at least go through the setup in detail, and then we'll just give you time, because I kind of think that once you get the hang of this, you can go through these and solve them all. So I'm kind of thinking that out of all these 7 problems, this will be another homework turn-in thing where I'm going to ask you for one of these. All right? So let's go ahead and just dive in with 13. So in 13, somebody already told us it's a 1 to 2. That was Julian, right? Okay, so that means we already know that the math, the way we put it together in our notes, it looked like this. Did we use 1 and 2 or A and B for the objects? We used 1 and 2. So we had M1 plus M2 times M. I'm just going to do it this way. 1, 2 initial equals M1 V1F plus M2 V2F. So that's the equation we'd be dealing with. Yes?
Is the M supposed to be a V?
The what?
The M, the third M?
Third M. Wait. Oh! I'm like, you said third, and I'm like trying to count them. See, now you caught me on tape being bad. That's what will make this more popular. I saw him make a mistake. Okay. So we're all set to go here. We do have to make a decision. Which object's going to be object 1 and which one's going to be object 2? And the truth is, it doesn't matter. So somebody want to just decide? Oh, it's a tough decision. Okay, Maria.
M1 or object 1 be the kangaroo.
Okay, so we're going to have 1 be the kangaroo. And that means 2 is now the log then. Okay? So now that we've decided that, somebody read the problem and highlight one piece of information they give us and what is the value and then what variable is it. Because if we're going to solve for one thing in here, that means we need to be able to put a number on everything else. Who's got something? Okay, Alexis. It's 250 kilograms. So, M1 or M2? M2. Perfect. All right, somebody else, give me another one. All right, Maria?
The final velocity of the log is 3.8 meters per second.
Okay. 3.8 meters per second. And you said this was the log, so what specific variable would it become?
Final velocity 2.
So it would be VF, V2F. Now there's one other key word that went with it. Do you catch something right before, there's a phrase right before the 3.8 meters per second? So how does that reflect here? It would be negative. Perfect. Very rarely, although it does happen occasionally, some problems will be very nice about giving you, pluses or minuses, but in some cases they'll try and challenge you a little bit by just saying things like opposite direction or in the other way or something like that, and you need to catch that because things can move in either direction. All right? Somebody else, give me another piece of information. All right, Julian?
V1F is going to be 14.6 meters per second.
V1F was 14.6?
Yeah.
14.6 meters per second. Okay. Do we have anything else? All right.
Would the initial velocities for the log and the kangaroo be 0?
Why?
Because they're just floating there.
Perfect. And this is what I was going to do next. If I looked at this, if you were to say, am I missing anything? We have M2, so I could make a little check mark here and here because I've been given that. I have V2F, so I'm good there. I have V1F, so I'm good there. And at this point, I would realize I'm still missing something. Because which one of the, if you're really good, you notice that I'm supposed to find the mass of the kangaroo, which is M1. Which means I still have an unknown here. And Maria picked up on that they said, oh, it's just floating there. And that means this thing that I call V12I is 0 meters per second, and I'm good. So now, what one other possibility, before I actually start to plug stuff in and solve, what one other possibility might I need to keep an eye out for that I might have to do before I start to plug stuff in? Anybody know what I'm thinking of? For example, what if I said the log was 120 pounds? What would I need to do before I started plugging numbers in? Convert to kilograms, because we need everything in MKS units. So keep an eye out for any conversions that you might have to do. Because remember, before you start to plug things in here, you need to have them in meters, kilograms, and seconds. Let's see, and we have, so are you guys okay getting 25 whole minutes of work time? Okay, because there's not much difference between what we just did here and what you're going to do on almost all of the problems. The equation might look a little bit different because it might be a different situation, but you need to work your way through like this. Keep your eye out for conversions, and I think Trevor mentioned the cow problem. The cow problem added one extra thing where it said, oh, you have a cow on a cart, and so they're not going to separate, so you just add their masses together to treat them like they were a single object to begin with. All right, so I'll give you guys the rest of the class period to work on this, and with the idea that somewhere down the road, I'm going to ask for one of these problems to get turned in as a homework problem. Any last questions? All right.